This slide summarizes the entire study. We investigate and posted cast iron as steel plate because ABC Engineering observed inconsistent performance. Through metallography and mechanical testing, we found that the material was an S-cast ductile iron with a ferritic-perilytic matrix. The high ferrite context helped explain the lower than expected mechanical properties. Based on those findings, we recommend better casting control, microstructure checks, and potential heat treatment. ABC Engineering faced issue with the imported plates, which show lower strength and hardness than expected, because cast iron properties depend heavily on microstructure. We need to examine the internal structure in detail. Research from 2022 to 2024 clearly shows how microstructure controls strength, which more ferrite means stronger material, while excess ferrite weakens it. This helps us understand the nature of the performance issue. These are the objectives guiding our investigation. We begin by examining the microstructure and then evaluating the mechanical properties. From this, we aim to pinpoint the reason for poor performance and develop recommendations for future quality controls. Finally, the project also helps strengthen teamwork and engineering analysis skill. Now, I'll pass to Dini.
For section 3.1, our testing plan consists of 4 major steps: metallographic preparation, chemical etching, optical microscopy, and phase quantification. We follow relevant ASTM standards, including E3, E407, E1182, and E562 to ensure accuracy and consistency. The purpose of this test is to obtain a smooth and scratch-free specimen surface, reveal ferrite, perlite, and graphite nodules using nitrile etchant. Observe the microstructure at 200 times magnification, and finally, we will determine the volume percentages of each phase. These tests are justified because ductile cast iron's mechanical properties are strongly controlled by its microstructure. Features such as the ferrite-perlite ratio and the shape of the graphite nodules directly influence strength, ductility, and machinability. Metallography is therefore the most reliable method to confirm whether the material meets its expectation classification and performance. For section 3.2, safety and laboratory procedures were strictly followed. Full PPE was worn, including lab coat, goggles, closed footwear, and heat-resistant gloves. General lab safety was maintained by tying back long hair, avoiding loose accessories, and keeping the workspace dry and organized. Chemical handling was done carefully, especially with nitrile, which was used only inside a fume hood to prevent inhalation and chemical exposure. We ensured the specimen was clamped securely during cutting, avoided touching hot surfaces during mounting, and prevented cross-contamination during grinding and polishing. During etching, only a small amount of nitrile was used, and the reaction was stopped immediately by rinsing. Lastly, the microscope was handled gently, with lens cleaning done using lens tissue only to avoid scratching. Overall, these procedures ensured both accurate microstructural analysis and a safe working environment. Chemical handling was done carefully, especially with nitrile, which was used only inside a fume hood to prevent inhalation and chemical exposure. We ensured the specimen was clamped securely during cutting, avoided touching hot surfaces during mounting, and prevented cross-contamination during grinding and polishing. During etching, only a small amount of nitrile was used, and the reaction was stopped immediately by rinsing. Lastly, the microscope was handled gently, with lens cleaning done using lens tissue only to avoid scratching. Overall, these procedures ensured both accurate microstructural analysis and a safe working environment.
And I will be explaining about the experiment that we have conducted through our lab. The first one is metallography. In short, metallography is an important part of material science that engineering focuses on studying the microstructure of material to understand their properties and behavior. Throughout the experiment, we have found that a few sample preparation. The first one is sectioning, which is done to cut the sample and separate the area of interest so it can be handled more easily. The next one is mounting, which is helped to protect sharp edges and surface features. The next one is grinding and polishing. This process involves gradually smoothing in sample surface. And the last one is etching, which is helped to reveal the microstructural features or faces inside a material. We have also included the sample before etching and the sample after etching in 50 magnification. The next one is tensile testing. Tensile testing is a common method used to determine how material behave when put through a pulling force. We have also included in this presentation the dimension of the workpiece. Based on our dimension, we have calculated the elongation and the reduction in area, which is for the elongation is 9% and the reduction in area is 31.6%. Also, we have also found the peak stress, the peak load, 2.0% offset yield stress, yield strength, and yield load, and Young modulus. And for this presentation, we also included the stress over strain graph for this material. The third one is hardness test. Hardness testing determines how material responds to an applied load from an indenter, which can be a diamond or hardened steel or tungsten carbide bore, depending on the test type. There are two main types of indenters, which is ball indenter that used for a softer material, and the diamond indenter used for hardened material. There are three types of hardness test, which is Brenner, Rockwell, and Vickers. And for our experiment, we have used Vickers hardness test. And from our experiment, we got the average hardness Vickers, which is 46.2, and we have converted to Brenner hardness, which is 233, and the Rockwell hardness, which is 99. Based on our experiment, we got the data summary table. For the experiment, we got the yield strength, ultimate tensile strength, elongation, and hardness of the material. We got 515 megapascal for our yield strength, which is slightly higher than the specification, and the ultimate tensile strength, we got 623 within a acceptable range, which is 689, and the elongation is slightly higher than the range, indicating a poor inductivity. And the hardness test, we got 233 within the expected range of height strength. That is all. Thank you.
Now, I will be presenting the microstructure analysis. The microstructure of ductile cast iron was revealed by etching in 4% nitre for approximately 2 minutes 30 seconds and observed clearly by specialized microscope by 50 times magnifications. And this shows the grain morphology. The graphite in the samples appears as spheroidal type nodules, type 1 nodules, which are uniformly distributed throughout the matrix, which indicating adequate magnesium treatment. The nodule count typically range from 80 to 150 nodules per millimeter square, and this depends on the cooling in some regions. The nodules are generally fine to medium in size, measuring approximately 15 to 40 micrometer in diameter. Secondly, the inclusions type. Scanning electron microscopy analysis typically reveals the presence of several types of inclusions and secondary phases in the material, like manganese sulfides are commonly observed in elongated or globular form. Outside inclusions such as alumina, silica, and magnesium silicates are frequently detected. It's formed during magnesium treatment. The defects. Common casting defect observed in this alloy include shrinkage porosity. The graphite degenerations may also be present. Then let's move to the mechanical properties. First, the tensile. The tensile falls within the range defined for common ductile ions grades, where tensile strength of 370 to 550 megapascal and hardness values of 130 to 220 are typically depending on the matrix structures. Secondly, the ductility. The presence of spheroidal graphite nodules enhance the ductility and toughness by interrupting crack propagation. Thirdly, the strength and hardness. The ferrite-rich matrix contributes to lower strength but improved elongations and impact resistance, while the pearlitic regions provide increased hardness and tensile strength due to the lamellar ferrite cementite structure. Lastly, let's look what correlations to the client complaints. The microstructure of mechanical results give a clear picture why the client may be experiencing failures in service. Defects such as shrinkage porosities, microporosities, and areas where the graphite has begun to generate can create a small weak spots that eventually grows into cracks under load. Second, the incomplete heat treatment. If the heat treatment is not well controlled, uneven cooling or incomplete ferritizing can leave the casting with areas that are softer or harder. Lastly, the chemical segregation. Chemical segregations during solidifications, particularly variations in carbon or silicons, can also cause uneven graphite nodules distributions, resulting in sections of the casting that behave differently under.
From our investigation, we identified 4 main root causes that explain the failures observed in the ductile cast iron component. First, casting defects such as shrinkage, porosity, and microporosity were found throughout the material. These defects create internal weak spots where cracks can easily form under load. Second, we observed graphite degeneration, where some spheroidal nodules change into vermiculate or chunky shapes. This is usually caused by magnesium fading or poor inoculation, and it reduces the ductility and fatigue strength of the material. Third, there were matrix inconsistency in the balance of ferrite and pearlite. This typically happens when the cooling rate or heat treatment is not well controlled, leading to inconsistent hardness and mechanical behavior across the casting. Lastly, we found inclusion contamination such as oxides, slag, and manganese sulfides. This inclusion acts as stress concentrators and further weaken the material during service. Overall, these combined factors explain why the component failed prematurely under real operating conditions. Next, I'll be talking about the proposed solutions. To improve the performance, strength, and ductility of the material, we recommend several solutions. The first is heat treatment optimization. Using a controlled normalizing or ferritizing process will help stabilize the matrix structure, reduce brittleness, and improve both toughness and consistency. Next, supplier and melt quality control must be strengthened. This includes ensuring stable magnesium levels, maintaining proper inoculation practices, and improving melt cleanliness. Doing this prevents graphite degeneration and reduces the formation of harmful inclusions. We also suggest considering better material options if the component will face high stress or fatigue conditions. Higher grade ductile irons, alloyed ductile irons, or even a tempered ductile iron can provide a significant better mechanical performance. Finally, we recommend conducting further validation tests such as SEM and EDS analysis, ultrasonic testing, radiography, fatigue testing, and hardness mapping. These tests will help verify that the improvements are effective and that the material meets performance requirements. With these solutions, the overall reliability, strength, and ductility of the component can be greatly improved.